Recording in progress.
So, okay, Olga, I see it's the time, so shall we start?
I think we should start. I don't see too many people. Maybe they are quite tight already. But okay, we should start anyway, I think.
Okay, so let's start. I'm Dawi Wang from Zhejiang University, and it's my honor to chair this session. Our first speaker is Professor Smirnova from Australian National University. She's going to talk about localized states in nonlinear and topological photonic systems. Please start. Daria?
Yeah, thank you for the introduction and thank you for the invitation. I will be talking about localized states in nonlinear and topological photonic systems. In fact, this is a rather broad topic, and today I will just discuss a couple of our results in this direction. So this covers a part of my research activities at the Australian National University, and I have also recently joined the theoretical quantum physics group at RIKEN in Japan. Before I start, I would like to acknowledge my collaborators on this work from Singapore, Russia, and Australia. So our studies in this direction are broadly motivated by topological photonics. The first review on this topic appeared in 2014, and in general, topological photonics concerns the study of engineered photonic systems, such as photonic crystals, with the so-called topological band structures, which are inspired by analogies with topological insulators in the condensed matter physics. And the hallmark of these materials is the ability to support robust boundary states, such as H or surface modes, protected from backscattering. For instance, this journal cover on the left illustrates such electromagnetic wave, which propagates along the edge of two-dimensional photonic crystal made of ferrite rods, and it bypasses this defect almost without back reflection. The existence of such edge states can be related to the topology of bulk bands in the reciprocal space, which in turn can be characterized by the topological invariance. For instance, denoted here by C, and as soon as this C is non-zero, we can expect the existence of such edge states as at interfaces. Such edge states remain insensitive to a range of perturbations, which is, of course, very appealing for applications in photonics and in optical communications. In turn, optical nonlinearities can lead to a plethora of interesting effects in topological photonic systems, which we described in our review paper published in 2020. Considering some historical trend, special efforts were focusing on miniaturization of topological photonic systems, starting from this magnetized array of ferrite rods in microwaves, then silicon ring resonators, waveguide arrays, and finally, topological photonic states can be brought down to the nanoscale in metasurfaces, which may represent arrays of resonant nanoparticles or nanopattern membranes. But one of the basic platforms for nonlinear topological photonics is photonic lattices based on waveguide arrays, made of waveguides, either helical or straight waveguides. And for instance, this triangle-shaped array here acts as a topological photonic insulator, so that the light is guided along the edge of this array and bypasses a defect created by missing waveguide. Paraxial light propagation in such waveguide arrays can be described by Schrödinger-like equation, which can be replaced under some approximation with the Kaplan-Meier theory equations, which describe the coupling of light between mesmeric waveguides. And what is important here is that the nonlinear regime is quite natural to consider at high optical powers, because in this case, the refractive index becomes intensity dependent, what is known as a Kerr effect, and this Kerr effect can lead to the self-localized nonlinear modes such as solitons. So from our own perspective, we studied nonlinear effects both in the bulk of topological photonic lattices and nonlinear dynamics along the edges. Quite interestingly, in some cases, bulk modulational stability can be used for extraction of topological invariance instead of tomography of bulk bands. However, today I'm going to focus on on our results on nonlinear dynamics along the at the topological domain walls. So indeed, it's interesting to explore nonlinear generalizations of topological lattice models, where we incorporate nonlinear corrections as field-dependent operators. Most of early studies in this direction were numerical. They were limited to some specific numerical solutions for specific lattices, and some works tried to apply the nonlinear Schrödinger equation for the effective description, but this equation is oversimplified because it disregards what happens in the direction transfers to the interface, and it's also completely independent of the bandgap properties. So we put forward our alternative universal nonlinear Dirac model, which allows to describe nonlinear dynamics in nonlinear topological photonic lattices in the continuum limit. So instead of the scalar Schrödinger equation, we use the vectorial Dirac equations. And speaking about the equation which is written here, we can construct our nonlinear Dirac model from the Dirac Hamiltonian made of sigma matrices, which act on the two-component spinor wave function, and here we also incorporate the local self-action nonlinearity. Additionally, we may include second-order dispersion terms on diagonal, which is relevant to Bernoulli-Furgent model, or on the off-diagonal, which is relevant to the trigonal working in graphene. So based on this model, we can actually make important explanations and predictions on linear topological photonic systems. For instance, 4 years ago, we obtained exact analytical solutions for the bulk solitons and nonlinear edge states. Solutions are given in this work, and as examples of particular implementations, we may consider one-dimensional system dimerized array, which is known as a Sushri-Verheugen model. It can be made of nonlinear resonators, or we may consider nonlinear photonic graphene with staggered sublattice potential. And the interplay of nonlinearity and topology in such systems can give rise to mutual transformations of localized states. So here is an example of spatial temporal dynamics in the continuum SSH model. So it seems that soliton is reflected from the edge, and the edge state gets excited. So this effect holds beyond the continuum limit, and here is an example of dynamics in finite discrete lattice. So the incident soliton excites and populates the edge on the non-trivial, the edge state on the non-trivial edge, while it is completely elastically reflected from the left trivial edge. Here's a zoom-in picture, what happens on the right edge. Here we see the low amplitude edge states, which completely resides only on one sublattice, in agreement with the known solution for the edge states in this model. This effect was experimentally confirmed by the group of Professor Zhigan Chen using the photorefractive crystals. Then, by analogy to one-dimensional case, H states can be excited on closed domain walls by scattering of the semi-vortex bulk solitons. Here you can see a clockwise pulse of the H state, which is excited on the circular control. This is the main wall. This soliton excites the persistent topological current and then goes away, tilted in the opposite direction. And we have also described the effect of gradient catastrophe for H wave packets at the topological valley-hole interfaces. And I would like to discuss a little bit more about this two-dimensional system and about this effect. So as a specific example, as I mentioned, we may consider this staggered graphene lattice. Here spin is just sublattice degree of freedom, and the effective mass characterizes the tuning between two sublattices. They're called in green and gray color here. From the tight bonding model of this lattice, we can go to the continuum limit, which gives us a nonlinear Dirac-Hamiltonian, so far linear Dirac-Hamiltonian, and the domain walls can be created by the mass inversion by the sign change of the sign across the interface. So this interface supports H states, which is localized in the transverse direction. It has linear dispersion and it resides in the bandgap. And next, we are interested how nonlinearity affects H states. So we obtained analytical solution for the nonlinear H state, which can be obtained from the standing soliton profile. And then we derived modified nonlinear Schrödinger equation for the slowly varying envelope. So this equation can be derived from the nonlinear Dirac model using the asymptotic series expansion of the spinor wave function. And in this asymptotic approach, we have two characteristic scales. The first one is the strength of nonlinearity compared to the width of the bandgap, and the second one is the dispersion. The dispersion is introduced for the photonic graphene by of diagonal second-order derivatives. In the first order, in this expansion, in this first series asymptotic approach, we assume that the dispersion is smaller than nonlinearity. So in the first order approximation, we get the nonlinear simple wave equation, which describes the gradient catastrophe. So it means that as the pulse propagates along the domain wall, its trailing wave front becomes increasingly steep and eventually developing discontinuity in a finite time. In the second order approximation, we derive our modified nonlinear Schrödinger equation, which contains this additional term. So we verified the validity of the derived equation by performing modeling of the nonlinear Dirac equation. So here we first of all neglect the dispersion and launch the pulse of the Gaussian profile. So if our input is Gaussian, then we can estimate the breakdown time analytically. And we see that the numerical solution plotted here with the blue curve agrees with the theoretical solution plotted here by red dotted curves. So the effect of a gradient catastrophe is clearly noticeable here. Then we also see that modified nonlinear Schrödinger equation, when now the dispersion is switched on, also correctly reproduce the growing asymmetry of the H pulse as it propagates along the interface. At the same time, if we use just the conventional linear Schrödinger equation, it shows only the compression and some focusing, nor this self-steepening effect. So to show that this is not just a theoretical curiosity, we perform modeling of the realistic Valley-Hall waveguide array with the parameters taken from this work. This is experimental paper, and the supercell of this array looks like this, and it supports the H states of this kind. Then we to simulate the beam evolution, we solve this Paraxel equation by propagating the optical beam in the periodic lattice. So this purple arrow shows the direction of motion. And here we clearly see the signatures of the gradient catastrophe development and notable distortion of the pulse. If we compare it to the linear propagation, to the linear solution, then we don't see any such effect. So our pulse doesn't change its shape. If we plot then the intensity map in XZ plane, where Z is the propagation direction and XZ is aligned with the domain wall, we also see at the initial stages of propagation, there is a growing asymmetry, which perfectly agrees with the solution of the nonlinear Dirac model. This self-steepening term can also lead to the separation of modulation instability for relatively high amplitude plane wave-like H waves. While a conventional nonlinear Schrödinger equation would predict the instability in both these two quadrants of the parameter space. So when our nonlinearity exceeds the dispersion, in principle, we may expect this stabilization effect for plane wave-like H modes. And we verified this our insight, theoretical insight, numerically. This way, again, solve the Paraxel equation. We see that for the linear, for the relatively low amplitude H modes, the instability develops as with time, while for the as we increase the amplitude at the plane wave at the interface, as soon as it exceeds some critical value, the H mode gets stabilized. So this is my concluding slide. Our approach based on linear Dirac model is quite instructive. It allowed us to obtain the exact analytical solutions for localized nonlinear modes, and also capture the effect of gradient catastrophe for H-wave packets which propagate along the domain walls, and predict the effect, self-steepening stabilization effect for plane wave-like H modes. With this, I thank you for your attention.
Thank you, Daria. So any questions? Well, I have a question. So this soliton state is different from the Su-Schrieffer-Hager model edge state. People sometimes also call that a soliton state. So this is
yes, I understand. So in principle, people sometimes call the linear solution of the SSH model is soliton or king state, but it's in the conventional SSH model without nonlinearity. It's just the a linear solution of this type, where we have the H mode residing on the one sublattice, or if we create an interface, it means that we create a principal domain wall. So we can also get the interface states, but this model completely doesn't include any nonlinear corrections initially.
Okay, great. So any questions? Okay, if not, so thank you, Daria. Thank you again. And Our next speaker is Professor Zhenbao Liu from the Chinese University of Hong Kong. His talk is quantum nonlinear spectroscopy via a spin sensor. Great.
So can you see my screen?
Yes.
Okay. So thank you, Dawei, for the introduction, and also thanks to Olga for the invitation. So tonight here in Hong Kong is the evening. So I'm going to talk about the extraction of arbitrary types of the orders of correlations using the spin sensor. We call this one quantum nonlinear spectroscopy. So the theory of this work was done by Ping Wan and Chen Cheng in my group, and also I have experimental collaborators in Stuttgart, Hefei, and also Hong Kong UST. So we know that in sensing, we're mostly interested in extracting information about the target systems. So the information basically is just statistics. In physics, we call this one correlations, such as the expectation values or the variance corresponding to first and second moments in statistics. Right. So this we know that it's very important to the understanding of foundation of quantum mechanics, such as in the Bayer inequality and also in the Nagel-Gager inequalities. In the classical world, when we consider the correlations of different quantities, such as the product of A and B, we don't make a difference between AB and BA because they commute. But in quantum mechanics, two quantities, in different orders, could have different, meanings. In particular, if we say that the two quantities do not commute, the commutator defined as A times B minus B times A may not be zero. The famous example, of course, is this commutator between position and momentum, that is I h bar, right? On the other hand, we can also define the so-called anti-commutator, which we denote as A plus B. That's A times B plus B times A. Right? So of course, if these two quantities are classical and commute, this will just reduce the normal product 2 times AB. And so we denote the commutator as A minus B. Okay. So if we consider n quantities, and then there will be n factorial different types of orderings. So this will form the so-called complete set of correlation functions. This basis is called a Whiteman basis. Right? If they are defined at different times, so then the particularly interesting one are those time-ordered correlations. So defined as these commutators or anti-commutators, between different quantities about the place in the time ordering format. Okay, but of course there will be also some this time ordering quantities operations will have altogether 2 to the power n minus 1 types. So that means that there will be n factor minus 2 to the power n minus 1 and other types of correlations which are called out of time order correlations. And this so-called OTOC actually are not observable in dynamics. Okay, so do not affect the dynamics at all. And so in this talk, I will mostly focus on the detection of those time-ordered correlation functions. These are 2 n minus 1 types of nth order correlation functions. So there's already some method to detect this kind of correlations, such as the conventional nonlinear spectroscopy. If we consider nonlinear objects, for example, and we have a classical field coupled to the dipole of a system. And then the response can be quantified by the average of the change of the dipole, which can be expanded in orders of this perturbation field E, right? In the first order, this linear optics, second order optics, and third order optics, and so on and so forth. And to evaluate this susceptibility chi1, chi2, and chi3, so we can not just use the very simple time-dependent perturbation theory, right? Starting from the state, we can do the first order perturbation, second order perturbation, and you can see that since this E is a classical number, so it can all be taken out of these commutators. So the only left things will be just the commutator between the dipole operator at different times. with the density matrix of the system. So that means, all this susceptibility measured by the nonlinear optics actually will be this simple commutators between the physical quantities at different times. Okay, so time ordered. Right. For example, if you look at the third order nonlinear optics, and then we have this third order susceptibility is proportional to the this fourth order correlation functions given by the commutators between D3 and D4 and D3 and then D2 and then D1, and they are the dipole operators at different times. Okay. So then that means there will be 2m-1 to the power m-1 different types of other correlations which are not accessible to this nonlinear spectroscopy. So how can we detect the other, actually the vast majority of those correlation functions? Okay, so that's the question. Okay, so the idea, the solution to this challenge is to use a quantum sensor, as I will explain in this talk. Okay. Right. So the basic idea is that if we look at the evolution in quantum mechanics, starting from any initial state, so there will be different order lengths, in the superposition to evolve from the beginning to the end, and then depending on how you choose the measurement basis, actually you are observing different types of histories. Okay. So this way we can actually select the effect of the interaction between the sensor and the target system. Okay. For example, if you consider the interaction between the spin sensor and comes to the target system through this spin operator SZ, the spin in the Z direction, and the magnetic field operator in the Z direction. Okay. So then if we can, for example, you prepare the spin in the X direction and then you measure this one in the Y direction. So this basically you are looking at the evolution of this spin driven by the field from the environment. So this is the one world view. Okay. But you can also measure the spin in another basis that will give us another world view. So if we prepare the spin in the X direction, then basically this is a superposition of the plus Z and minus Z states. So if we measure this sensor spin in the Z direction, this actually gives us the field, from this spin, and then we are looking at the evolution of the environment driven by the sensor. So these are just two different world views, right? Just chosen by measuring the sensor along different bases. Right. So mathematically, so we can say that if we have an initial state of the sensor state coupled to this target state rho b, and then we have the interaction between the two systems through this sensor operator and the target operator b, and then you can see that now this force is a kind of a quantum force. Okay. So the evolution again is given by this newer equation. Okay. If you look at the very short time evolution, this can be determined by the perturbation for the first order. Right. Now we can remember this V contains two operators S and B from the sensor and the target respectively. So we can decompose this one into two factors, two terms. The first one is that contains the commutator between this S and the state of the sensor, and then times the commutator between this field of the target and the target state. And the second term just the commutator between the sensor operator and the sensor state times the anti-commutator between the target operator and target state. These two terms actually have a different physical meaning. Okay, so if you look at the first one, let's take the trace, for example, of the sensor. You can see that this anti-commutator basically just provides the average of this sensor operator. So this basically we are viewing this sensor as a force acting on the target. So the target will evolve, driven by this force. And then, so we have the evolution just given by this the commutator, right? So the second term will be just the back action. So this, in this case, the target now as a force, act as a force, driving the evolution of the sensor. Okay, right. So this is just two different terms. And now, as we have seen earlier, so we can design the initial state of the sensor and choosing a basis. So we can choose one of these two terms to be realized. In particular, so we consider spin half sensor prepared initially in the x direction, for example, and this sensor is coupled to the text through this operator SZ. So if we measure this sensor spin in the z direction, so we are basically looking at the a kind of a classical force from this sensor, and then we're looking at the evolution of this target state under this classical force, right? So mathematically, so you look at these two terms, right? So we have decomposed the evolution into these two terms, and then you take the you do the measurement of sigma z, or the z direction. So you times this one to SZ and do the trace. You find the second term will just be 0, and the first term will just give us the evolution of the commutator between this target operator and the target state. And similarly, if we prepare the sensor spin in the x direction and then measure the y direction, we are basically looking at the rotation of this sensor spin about the z direction. So in this case, of course, the target system would act as a force. Okay. So mathematically, we look at these two terms and we measure SY, right? You put SY right here and do the trace. You find that the first term will be 0, and then we are left with the second term, which is just you have the commutator between this sensor operator and the sensor state, and then times this commutator and anti-commutator of the target, which actually means that a force coming from the target. Right, so we can combine, a sequence of different shots of measurement with the initial state and the measurement basis designed. So this way, and then we do the coincidence counts. And so from this one, we can actually choose to measure arbitrary type and arbitrary order of the correlations. Okay, choosing this one to be commutator or anti-commutator between BK, BG, and BI. Okay. Right, so this way we can realize the extraction of arbitrary correlations. Right, so one example is a very simple one. We just prepare the sensor spin, such as the spin of electron waxing center in diamond, in the x direction, and they measure this in the y basis. So this one, as we said earlier, we just measure the field from the environment, such as a carbon-13 spin. So we can have a sequence of this one, and then we can take two of them to do the correlation. Okay, and then do the Fourier transform. This will give us just the usual noise spectroscopy. Okay, right. So using this method, we actually realize the detection of the resonance of a single carbon-13 nuclear spin with very high resolution. Right, and also we can use this method to distinguish, the noise of different natures, such as a random AC field. Quantum noise. So if we look at the random classical force, we know that in the fourth order, so the only non-zero, non-vanished term will be this terms that contains only anti-commutators, because all the commutators will be 0, right? So in this case, we look at the fourth order correlation function, we find that we have some peaks in this two-dimensional spectroscopy as a spectrum. But however, if the noise is from a quantum target, we have not only this classical type of noise, we also have this noise correlations that contains commutator and anti-commutator. So then we have two terms, okay, with one contains only anti-commutators, another one contains also two commutators. So from this one, you can see that this spectrum actually will present qualitatively different features. For example, in this case, we have 4 peaks around the center, and in another one, we have only 3 peaks. Okay, so also at different locations. So this gives us qualitative, features to distinguish classical noises and the quantum noises. Right. So we can use this one. So now imagine that we have a quantum target to probe. It has a frequency, right? So if we do the usual noise spectroscopy, we have this peak, right? So that's we have seen in the case of detection of carbon-13 nuclear spin. But in the real experiment, there's always classical noise from the environment. So put these two together. So what we usually get in the experiment is a curve like this. So it's very difficult, almost impossible to tell which peak is from the target, quantum target, which one is from the environmental noise. But if this environmental noise is classical, and then we can choose to detect the quantum correlations, and then the classical noise background will not contribute at all, right? So if you look at this fourth order quantum correlation functions, for example, and for the classical noise part, it will be always 0. So in this case, we will only see the peak from this quantum target, right? So we actually calculate the signal to noise ratio in the second order classical correlations. We found that in this case, when the background noise is too strong, as shown in this vertical axis, or if the quantum signal is too broad, as shown in this horizontal axis, so we have a so-called blind zone. In this case, no matter how long you do the measurement, the signal to noise ratio is always less than 1. Okay, so this means that we have a classically undetectable regime. Okay, so the quantum target will be always hidden in this background. But however, if you look at these fourth order correlation functions, and then no matter how strong is the classical background noise and how broad is this quantum target, we can always make the signal to noise ratio greater than 1 by just making the measurement time longer. Okay, so that means we can always single out a quantum target from a classical noise background by using this fourth order quantum correlation measurement. Right, so we actually have demonstrated this method in experiment by measuring this classical correlation, the quantum correlation, and from a random noise of the environment and also from a nuclear spin. We can see that as you see that in this bottom figure. So if we do the usual classical noise correlation measurement, actually we cannot distinguish, we cannot find out the nuclear spin, in this background, okay, as shown in this red curve. But if you look at this blue curve, which measures the quantum correlations, you can see that there's only contribution from this nuclear spin. The background noise is totally eliminated. Okay. Right. So so far we have talking about the detection of this correlation function use a single spin as a sensor. But in many cases we don't have access to a single spin sensors, such as in the liquid state MMR. We have actually an ensemble of sensors. Okay, and this of course is more convenient to use. But on the other hand, we also have this scalability problem. Okay, because if you look at the any independent sensor spins with very weak signal from each of them, and then the total signal of the case order correlation functions will be actually very weak. Okay, right. So this one will scale in the order of 1 over n to the power k. Okay, so it's for the MMR cases, this will be very small. So we actually invented a new method to extract the high order correlations. So instead of do k-short formation, we use the quantum channels, by technically called a phase cycling, to eliminate a certain kind of unwanted histories or word lengths, and only do one short formation at the end of the sequence. So this way we can also detect the high order correlation functions using the ensemble sensors. Okay, so we actually have realized this one using the liquid state MMR by detecting the fourth order correlation functions. Okay. Right, so this brings us to the summary. So we have come up with this idea and the theory of quantum nonlinear spectroscopy using sequential weak measurements. Okay, so to detect arbitrary types and orders of correlations of quantum targets. Okay, so one application of this one is to detect a quantum object totally free of classical noise background. Okay, we also generate this idea to ensemble quantum sensors by using sensor-sized channels instead of using many sorts of correlations to select different evolutions. right? So this can be generalized to test, for example, the quantum foundations, as we can now see that the classical objects and the quantum object can be actually totally distinguished by using those higher order correlations. So we are working on this so-called higher order negative Gaussian inequality. And this could also provide a new approach to studying quantum many-body physics. And we are also considering new types of sensors, such as light polarization, neutron spins, and so on and so forth. Okay. So thank you very much.
Thank you, Rimbo. Very nice talk. Any questions? So Professor Liu, I have a question. So you mentioned this classical noise, but actually everything, all the noise actually are given by essentially quantum system, right? So how do we define the classical over here?
Yeah, that's an excellent question. Okay, fundamentally everything is quantum. But when do we consider a system as classical? So basically, if you look at a classical magnet, for example, it's composed of many spins. And all of these spins actually are more or less independent of each other. Okay, so in this case, if you look at the commutators between the total magnetization, you find that the commutator between different spins will be zero, right? Because they are independent of each other. Okay, so that means you look at the total magnetization, that will be m. That's the number of spins divided by n squared, right? Because each one will contribute the signal of order of 1 over m. So that will give us almost zero when the m is big enough. So this means if you have many small quantum or many weak quantum signals put together, if they are independent of each other, not correlated, and then they will behave like a classical quantity, because the commutators between them will be just zero, or in the order of 1 over m. So,
okay,
so the basic idea is that you have many weak quantum objects independent of each other, and then they collectively will behave as if it's a classical.
Great. So actually, your formalism developed over here is essentially useful for those strongly correlated systems with
yes.
coupled
So
together.
especially if we look at the higher order correlation functions, they actually usually vanish for many-body system. But if we look at a system close to the critical point, for example, and then the correlation length will diverge. So in this case, these higher order correlation functions will be important, because the spins at different locations will be correlated.
Great, thank you. Any other questions? So if not, thank you again, Professor Liu. And our next speaker is Professor Chen Li, also from the Chinese University of Hong Kong. She's going to talk about non-local deformation sensing using nanodiamond quantum sensors. Please. So Chen, I think you are still muted.
Yeah, I'm here. Trying to sharing my screen. Okay. Can you see my sharing of the screen now? Okay, great. Thanks, Dawei, for the introduction, and thanks, Olga, for inviting me. I shall be talking about developing diamond-based orientation sensing for cell mechanics study. So I'd first like to acknowledge our students and postdocs. So the work has been done in our CHK quantum sensing group, co-led by Professor Rimbalu and myself. And the credit should really go to our students and postdocs for their hard working and continuous effort. Also want to thank the funding support and also a lot of contributions for our external collaborators. So I guess for the audience here, a lot of you are very familiar with the nitrogen vacancy-based quantum sensing using diamond. So I will skip most of the background, but just like to point out, right, the features of the NV-based comp sensing have a very nice match with the needs of the life systems, right, and making them very valuable sensors, right, to find out interesting properties in these life systems. Then a number of different biosensing applications ranging from endogenous temperature variation to detection of biomolecules have been attempted by using NV electron response to changes particular to temperature, the magnetic field, and nuclear spin. Since its first demonstration, the field of NV-based sensing has made a lot of progress towards real biological applications. While the early works has been focusing on demonstrating that NV-based method can be carried out in the biological environment or to measure bio-related parameters in a simulated or modeled biological system. Now the field is moved to real life systems and try to correlate the sensing measurement to physiological changes of the systems. And with a lot of them focusing on thermal sensing. But today, my talk will be mainly focused on NV-based sensing for biomechanics measurement. So the mechanics study is based on the deformation measurement, which is enabled by the NV-based orientation sensing that relies on NV electron response to the magnetic field. Here I put down the energy diagram of the ground state NV electrons with a negative electron, with a negative charge. The NV ground state is a spin triplet. And in the presence of the B field, the original degenerated M plus minus 1 will be splitting. This is Zeeman splitting. And accordingly, in the ODM spectrum, you would expect to see the single dip split into 2, and the separation is proportional to the B field. So this B field is not any B field, but the one projected to the 4 NV axis that can be taken for the 4 crystalline direction, 4 crystalline directions of the diamond. So now we can imagine if we have the B field fixed, and then the diamond containing NV that is changing its orientation, then this is equal to the effective B field projected to NV axis or different. Then you will be able to see changes in the ODMR spectrum and thus figure out the rotation or the orientation change of these diamonds. So this method, all right, commonly known as the vector magnetometry, is if you want to figure out the full information of the rotation of the diamond, you need to apply 2 B field of different orientations. Because if you have apply only one, then if this diamond is rotating about the B axis, you won't be able to figure out the difference. In fact, the first proof of concept demonstration of the nanodiamond rotation tracking dates back to 2011 by an Australian group. Then they tracked the angle change between the applied B field and NV axis. While later works show that the 3-dimensional rotation tracking can be realized in both the confocal and the wide field setting and disclose the features of diamond rotation on live cell membranes. Now, using the same principle, what I will be discussing today is by integrating the nanodiamond-based rotation sensing or orientation sensing with the atomic force microscope indentation, we can measure the non-local deformation for biomechanics study. To carry out orientation sensing, one needs to calibrate the B field, and this can be done by rotating a piece of diamond sample of no orientations. And in the same experiments, one will be able to figure out the sensitivity of the orientation sensing, which is about a couple of degrees per square root per Earth. Then we can measure the orientation change of the diamond, but how does that correlate to deformation of the surface? The idea is actually simple. So you will preload some of the diamond on the surface. Now, if the surface buckles, then these diamonds expected to change its orientation. And by figure out the orientation change, you would be able to reconstruct the surface deformation profile. So this is done by integrating the atomic force microscope indentation with the nanodelma orientation sensing. So the AFM creates a local impact, and the Delman sensor pre-anchored in the vicinity of the indentation, right, like this, will be rotating. And by recording the corresponding ODMR under two different B fields, with and without the indentation, one can figure out the full set of information of the rotation of the ND sensors, and then reconstruct the surface deformation. So here we call it a non-local deformation because what we measured is the entire surface in comparison to the local indentation and the displacement caused by the AFMT. The original thought behind this development of this so-called non-local deformation is really try to validate the different models when we use the AF indentation to interpret the mechanical result. And here is an example. So here we see by using either the JKR model or DMT model for the local deformation, low depth profile by AFM, you can have exactly the same fitting, but different parameters. But then if we're going to look at the non-local deformation away from the indentation location, right, the different model differentiates. So originally we thought we might be able to use the non-local deformation data to validate which model to use to interpret the mechanical data. So this is a bit of the work we done earlier back in 2019 using the AFM and nanodelman-based orientation sensing. So here we placed a single delman in the center and moving the AFM tip right in the vicinity of the ND sensor in a programmable manner and record the rotation of the ND. Right. So the sample we use in this case is PDMS, which is a polymer. Right. We oxidize the surface of the PDMs by ozone so that we create a bilayer structure. And we locate the nanodelman on the surface and carry out this rotation sensing. Right. So let me just get to the results. Right. So we can figure out the rotation angle, right, of all of the delmans, right, at a distance away from the indentation location and plot it out, right? So in this way, we can figure out the deformation of the surface away from the indentation location. Now, if to compare with the local indentation data by the AFM, right, we use two different models to fit it, right? One is the linear elastic Hertzing model with a single layer, and the other is to use the real case two-layer models. So in both the local indentation and the non-local deformation measurement, with only the two-layer model have the best fit with the data, but not the single layer. So this experiment just demonstrates, this non-local deformation method is valid, right? But you would say, but in this case, even the local data would be able to validate which model can be used. That's true. But then we're not always so lucky. Now, in this case, on our next trial on the gelatin hydrogel, we see that the two model works without consideration of a surface tension, right? In the modeling, you see in this local deformation, you can fix the data with or without consideration of the surface tension, but then in both cases, that will give you very nice fit, but obviously with different mechanical properties of the materials. But then if we're going to look at the non-local data, here we see the deformation. The experimental data can only be fitted with the model considering the surface tension. Now, at this point, we started to realize that the advantage of non-local deformation is beyond fitting model validation, but much more generally, as the non-local deformation itself is only determined by the applied load and the material mechanical properties, but not on the local interaction between the tip and the sample in the linear elastic regime. In fact, people have adopted method, this non-local deformation using the fluorescence microspheres to carry out the non-local deformation to study the elastocapillary effect of materials, which actually refers to the computation between the material elasticity and the capillarity or surface tension. The computation is described by the so-called elastocapillary length S, which is defined as the surface tension divided by the elastic modulus. Right? If the deformation measurement happens at a length scale much smaller than the elastocapillary length, then the capillarity take a lead. Or if you have a length scale much larger than the elastic capillary length, the elasticity will take the lead. Only at a measurement range, which is comparable to the elastocapillary length, then you can see the contribution from two of the contributors of both capillarity and elasticity. Then this principle makes the Dellman-based non-local deformation sensing particularly attractive for addressing the elastocapillary effect in bio-relevant materials. This is because these soft materials usually have elastocapillary length in the range of hundreds of nanometers to a couple microns. And the conventional non-local deformation does not have the spatial resolution. On the other hand, for softer materials, for this mechanical measurement, we usually want to use shallow indentation, right, for the minimum invasion or destruction, so that the nanometer scale sensitivity for the deformation is needed. And both requirements can be nicely satisfied by using the nano-Dellman-based non-local deformation sensing. So with that, we move to the fixed cell in our next project, right? And both surface tension and the Young's modulus can be obtained by feeding the non-local deformation data as shown here. I'm going to skip this part of the results, but just show we actually carried experiment in two different types of cells. One is a normal cell, is a HeLa cell, is a cancer cell, but without a special treatment. So we fix the cell and make the measurement. And in the other group, we have used the cytoclastin D, which is a chemical that will depolymerize the actin cytoskeleton in the cells. So the cells will become softer before being fixed, right? So by looking at the comparison of the data, we see very interesting results using the non-local deformation. Now here, the blue dots are the mechanical data or elastic modulus of the fixed cells obtained by the local AFM indentation, right? And this is the result obtained by the local indentation. So this is the normal cells, right, without the cyto D introduction. And this is the set of the data that obtained from the non-local deformation. You see, without the consideration of the surface tension, the elastic modulus is always overestimated. Then we look at the data for the cytoclastin D treated sample. The similar phenomenon happens. That is, without consideration of the surface tension, the AFM-based method tend to overestimate the Young's modulus. But then, if you look at the difference where the cytoclastin D is introduced, in both cases, because the actin cytoskeleton is depolymerized, so the cells become softer, and you see the Young's modulus indeed decrease. But then, if you look at local versus non-local data, this decrease is underestimated if the local indentation data is used. Right? Now, colleagues might get a bit of impatient saying that, that's great method, but that when would you be able to switch to real live cell measurement? The answer is that's difficult, right? And the difficult lies in, think about our method. Our method is done by assuming that you give a mechanical stimuli to the cell, then the response you measure is coming from that stimuli. But what happens in the live cell is that, so these are images of live cells, and the red spot are the fluorescent signals coming from the nano-Dellman. So they come from the medium and eventually anchored on the membrane. Then they're still like shaking a little bit, right, with a bit of the translation motion. But what is the most problematic is that if you look at these nano-Dellman, they rotate a lot, even without any mechanical perturbation, right? So now we have a problem. We won't be able to figure out which rotation comes from which whether this is the lifestyle activities cause the rotation, or this rotation is induced by the mechanical stimuli. How to solve this problem then? Right, now we have a possible solution, right? And the idea was borrowed from the from the dynamical mechanical analysis when the oscillatory load is introduced onto the sample at a specific frequency. And this method has been used by the AF-based indentation for assessing the viscoelastic property of materials, including the live cells. So now one can imagine once the oscillatory load is applied, that it will cause oscillatory deformation at the indentation location. But then at the location away from the indentation by the stelment, you will see the oscillatory rotation as well. Right now, of course, right, for each of the either the depths or deformation at the indentation location or the rotation of the delment, there will be a phase delay, right, or phase lag compared to the load that is applied. Now, what we thought is that we can measure, right, the rotation of the nanodelment, though there could be contributors from the lifestyle activities or other perturbations in the environment. But then by only extracting the signal at the same frequency of the oscillatory load, we will be figure out the response of the ND rotation to the mechanical load. To do this, we have to realize two things for the instrumentation. One is to synchronize the AFM ODMR, and the other is that because now we're going to do this experiment in the frequency space, so we have to speed it up the rotation measurement, which was actually a very slow one. Right. What we did is that we have used a 2-point ODMR measurement with 4 microwave exciting MV along all 4 directions to increase the signal-to-noise ratio, and also simplify the rotation amplitude estimation by calibrating to a non-rotation induced by the AC magnetic field. Right, now here's the data. And again, we first go back to a system, which is a static system of PDMS, right? Just to have a trial to see if this method is working, right? So here we apply, this is the sensor element, and then we apply the local load by AFM tip at the locations marked by the blue dot and the red dot. And here's the data. So the orange one is the oscillatory load, right? It happens at this frequency, right? And the blue one is the local depth profile, which have a phase lag to the orange one, right? And then the red signal or ODMR signals coming from the rotation of the delment, then we will be able to extract the green one, which have the same frequency as the oscillatory load, right? And with that, we'll be able to figure out the magnitude or amplitude of the rotation delment, as well as the phase lag of such rotation in response to the mechanical stimuli, right? And this is part of the interesting result. Other than the elastic modulus that can be attracted, we see the amplitude is always lower than the elastic modulus obtained from the local AFM indentation, right? So this is consistent with the static data I showed before. Now, what's more interesting is we can also obtain the information of the loss angle, which is a physical parameter describing whether the material is more liquid-like or more solid-like. So for small loss angles, the material is more like a solid. For large loss angles, the material is more like a liquid. Now what we see is that, right, using the non-local deformation, the data is a bit scattered, but basically goes the same trend as the bulk materials measured using the rheology. But if you use the AFM indentation to analyze the local data, what you're going to have is an underestimation of the loss angle. So in other words, using the local deformation by AFM, the materials looks more like a solid, but in the real case, it looks more like a liquid. Now, finally, this is a set of data carried out on different life cells, right? We basically see very similar trend. We see the spatial spread of the phase lag, right? If the delment are located at different locations away from the indentation, right? We also see an overestimation of the elastic modulus in the AFM case if the surface tension is not considered, as well as the underestimation of the loss angle without considering the surface tension. Now, with that, I'd like to summarize my talk. All right, what we did is that we have built up an integrated AFM and rotation sensing for non-local deformation with high sensitivity and good spatial resolution. This adds to the toolbox, right, for mechanical study of biorelevant materials, and also brings new understanding for the biomechanics. Thank you.
Thank you, Professor Lee. So any questions? Well, okay, please.
Yes, hello.
Hi, Miloš.
Hi, Chancellor. Thank you for a very nice talk. It looks like a very promising tool for biologists. I'm wondering, for example, so what you calculate is a strain based on basically rotations and etc. But the diamond itself, the grain of the diamond, it can have also some strain, right? For example, when it's incorporated in the cell membrane, so it can induce some strain. Would it be also possible to detect or separate this strain from diamond, nanodiamond, from biological environment?
So you mean if the diamond itself creates some strains to the sample,
Exactly.
whether that can be separated? We haven't thought about that yet. Actually, the interaction between the nanodiamond on the cell membrane, so with the cell, is actually much more complicated than what we thought, especially when the AFM indentation is introduced. Right, so this is probably the first step that we can sort of differentiate, you know, the live activities induced the rotation, as well as from that of the mechanical stimuli induced the rotation. But then what we see is that when we use the AFM probe to poke the cell only very mildly, sometimes the diamond can stay on surface just, you know, for us to take the whole measurement. Sometimes the diamond sample just get lost, right? What we suspect is that they actually enters the cells due to some of the stimuli. So for your question, I'm afraid I don't know the answer at the moment. Probably we're going to need a number of control experiments to figure out, you know, what really happens when you have both diamond on cell membrane, right? The biological interactions, as well as you add a mechanical stimuli, what would be the ultimate effect on that?
Right. Okay. Thank you.
Well, thank you for the nice talk. Our next speaker is Professor Lu Qiyuan from Shanghai Jiaotong University. He's going to talk about studies of synthetic frequency dimension in two coupled rings. Well, he could not give the talk in person because he's now on the train. So I will show his video yeah.
Thanks, Chairman, for the introduction, and I also thank Olga for the kind invitation to give me the chance to give a talk on our recent progress on the synthetic frequency dimensions. And I'm Lu Qiyuan, and I come from Shanghai Jiaotong University. So in this talk, I will share with you our recent work on two-ring systems in conducting the synthetic frequency dimension. And I will briefly give an introduction here and then talk about the experiment work and then the theoretical progress. So we know that in photonics, we usually requires the geometric dimensionality for controlling the light. Let me give some examples. For example, for this one-dimensional waveguide, the light are confined inside this waveguide, so the light can propagating through the waveguide along the z direction. Usually, we treat this system as a one-dimensional system. However, if we think about a one-dimensional Maxwell equation, we found that the one-dimensional Maxwell equation is very similar to time-dependent shielding equation, as the z here can take the part of the time evolution in the shielding equation. So therefore, this system where the light propagating along the z direction can be treated as a zero-dimensional zero-dimensional system for the quantum simulation of shielding equation. So as following this logic, if we consider a one-dimensional waveguide array, this system can usually be considered as a one-dimensional tide-bending lattice. Here, it can describe some one-dimensional Hamiltonian of interest. And here, each side corresponding to the light inside a particular waveguide, and the light between different waveguides can penetrate through each other through the evanescent wave. So therefore, it mimics the wave packet of a side can copying to a nearby side, and therefore construct a tide binding lattice here. So we can see that if we want to simulate some fascinating physics in photonics, we usually want high dimensionality, meaning that the system will be more complicated. And we usually want a complex coupling, meaning that the coupling is not a real value. For example, we want some complex values, and we also want some long-range connectivity. For example, this side can couple with a side which is not nearby. And we also want the system has some reconfigurability. So if we create some device, we want the system can be generalized to more functionality. So all of these requirements is kind of difficult to be easily achieved in traditional photonic devices. However, the synthetic dimension can give us a very good solution here. The idea of synthetic dimension is that if we can find a set of physical states which are discrete in a physical picture. For example, these are discrete physical states here. If we find a way to connect these discrete physical states in an order, then we can create a synthetic dimension here. So this idea has been previously used in the Cold Atom Society, where they found that in a one-dimensional atomic array, they can use the atomic state, in the degree of freedom of the atomic state, to create an additional dimension here by using the Raman transition here, so that in a one-dimensional atomic array system, they can create a synthetic two-dimensional space. More recently, Professor Wang from Zhejiang University has also proposed they can use the so-called superradiant state in hot gases to create such synthetic dimension and explore fascinating physics there. And in photonics, we usually think that there are, in general, 4 ways to create the synthetic dimension. The first one is use the time degree of freedom of the light. The researchers found that the arrival time of each pulse inside of the fiber ring can give a mark of the site number, so that they can create the synthetic dimensions through the time information. And people also realize that the optical angular momentum can also be used as a discrete physical site. And then they use external couplings to connecting these orbital angular momentum to create an orbital angular momentum dimension. And the researchers from Israel also proposed they can use the modal dimension to create the synthetic dimension. And in this experiment work, they proved the first topological insulator with the synthetic dimension in 2019. And our work mostly focuses on the frequency degree of freedom of the light. And we use a different frequency mode in a ring resonator to connect them and create synthetic frequency dimension there. And we found that this system can give us the capability towards higher dimension, and it can provide us complex coupling and long-range connectivity, as well as reconfigurability. So if you're interested in the synthetic dimension photonics, I encourage you to read all these review articles, and you can see that this field is gradually growing as the review article is published once every year. So in our system, what we consider is a very simple ring resonator system. And we found that if there is no group of velocity dispersion in the ring waveguide, then this system can support a set of discrete resonant mode with resonant frequencies equally spacing between each other. So therefore, in this system, if we introduce an electro-optical modulator inside the waveguide, then the light propagating through this electro-optical waveguide, it will carry a sideband informations. And then if we tune this modulation frequency to be equal or near equal to the frequency spacing between the resonance mode, then this EOM can connect all these discrete physical state in the frequency dimension. And then a one-dimensional lattice structure is therefore constructed in the synthetic frequency dimension. Here, the phase information actually turned out to be very important here, as the modulation phase can play a gauge degree of freedom, which can create effective gauge potentials and used for study the topological photonics. And moreover, if we write down the Hamiltonian of the system, we found that the simple system is mimic a one-dimensional tight binding lattice Hamiltonian here. So we know that this Hamiltonian take a Fourier transform. It will give us a band structure with a cosine shape band structure here. But here, the important thing is that the momentum dimension here, or actually the synthetic momentum here, is reciprocal to the synthetic frequency dimension. So it gives us a time information. So from the calculation or the simulation, we found that the band structure actually laid on the time dimension here, which corresponding to the single round trip times inside this ring resonator. So in experiment, we can take a ring resonator and use two waveguides to couple this ring resonator, so that on the one input part, we scan the we scan the frequency of the input light, and on the output side, we can take the transmission spectra, and then we can rebuild the band structure corresponding to the cosine-like band structure. So after the brief introduction of the background of the synthetic frequency dimension, let me show you some recent progress in the experiment part and also the theoretical part. We first studied two ring resonators with one ring is larger than the other one. So we choose the size of the larger one is twice as the small one, so that the frequency spacing, the small one, is twice as the frequency spacing of the resonant mode in the larger one. So in this case, only one of this resonant mode in the larger rings is resonant with the resonant mode in the small ring here marked as the yellow one. So in the larger ring, we add the EOM to moderate it at the frequency at omega divided by 2, so it can connect all these resonant mode in the larger ring. Therefore, this system constructs a leaf-type lattice in the frequency dimension. And the leaf-type lattice can support three band structure here, but the important information is that the middle one is a flat band corresponding to a balanced distribution of the eigenstate in the mode B and the mode C. And we will see the feature of this eigenstate distribution in the experiment. In experiment, we use two fibers to create these structures, and we use a set of waveguide to connecting with these fiber rings to input the signal and read out signal. We found that if we inject a signal into the B ring and read out from the B ring, then the band structure we explored is actually a projection of the band structure on the mode B, or actually on the mode, the yellow mode here. But on the other hand, if we inject the signal into the larger ring and collect the signal out of the larger ring, then we can observe the band structure projected on a superposition between the A mode and the C mode. So this is a experiment setup, and in the experiment result, we can find that if we inject the signal into the small ring and read out from the small ring, we can see that initially there is only two bands because of the A and B are largely coupled together. It introduces mode spacing, mode splitting there. So we can see two bands there. And if we turn on the moderation, so the system become a one-dimensional Lie lattice system, then it will have three bands, and the middle one has the flat feature, which here we can see it projected onto the mode B. And on the other hand, if we inject the signals into the larger ring, we can see that when we do not turn on the moderation, then the system has three bands here, where the first two bands corresponding to the mode splitting between the coupling from the coupling between the mode A and the mode B. And the mode C here is separate in the frequency dimension, so we can only observe a single band here. But once we turn on the moderation, the system again become a one-dimensional Lie lattice. We can see the interesting feature is that on the here we can see three-band structure, and the middle one has the flat feature. And more importantly, the upper one has only two bands, and there is no middle band. Remember that I said that the flat band actually corresponding to the eigenstate distribution on mode B and mode C. There is no any distribution on mode A. So therefore, if we inject the signal and scan the frequency near mode A, we cannot see the middle flat band projection here. And this flat band can also show a very different localization feature compared to the dispersive band. And moreover, if we add the large moderation frequencies to connect the to create the long range coupling, we can actually transit the system from a flat band feature to a non-flat band feature. So this work showed our capability of constructing different synthetic lattice in multiple rings. And in the second work, we take a step further and consider a two ring resonator with the same shape. And we know that each ring has a separate resonant mode as shown in this picture. And because we have two rings, two identical rings, then those modes are coupling strongly if we add the coupler between two rings. Then the mode in two rings will get splitting. So it will have two different resonance supermodes here labeled by this blue dot and this yellow dot. And we can say that the splitting is the 2 kappa. Then because the FSR in this ring is omega, then the spacing between this yellow one and this blue one is omega minus 2 kappa. So in this case, we can see that the splitting, the frequency spacing between different supermodes in the frequency dimension is no longer equal. And we can introduce two moderation frequencies with one omega 1 is exactly 2 kappa, and another one omega 2 is exactly omega minus 2 kappa. So then the first moderation part will give us a connectivity between those two modes, and the second moderation will give us a connectivity between these two modes. And these two moderation strengths can be different, meaning that the first one can have a strength G1, and the second one can have a strength G2. So this system actually give us a SSH model, a topological SSH model in the frequency dimension, and depending on the different strengths between G1 and G2, the system can be either non-trivial or trivial. But the problem from a traditional SSH model is that the band structure looks like exactly the same for the non-trivial one and the trivial one if we change the strength of G1 and G2. So the question is that if we can directly measure the topological feature, or we can say the system is topological non-trivial or trivial from the band structure measurement without going to the boundary to check the edge state. So in experiment, we use the fiber to perform this study, and we can see that the non-trivial case and the trivial case, the band structure looks like different in our case, because in our systems, all the frequency modes carry the resonant frequency information. So when it takes the Fourier transformation, all this information is imprinted in the band structure information. And we can take the band, do some calculation there, and we can extract the Z phase directly from the band structure. And we can see the clear difference between the non-trivial case and the trivial case, where the non-trivial case, the Z phase go from 0 to pi, and then from minus pi to 0 again. But the trivial case, the Z phase is going around the 0 part. So in this work, we show the capability in the synthetic frequency dimension to extract the topological environment directly from the band structure. We also conduct some theoretical work recently. People are interested in the photonic Moore lattice because it's in the condensed matter physics, the Moore lattice magical angle shows very important applications in the future. And in photonics, people want to do the quantum simulation to understand the Moore physics. But in most of the photonic systems, the coupling between different layers is kind of difficult to achieve. However, we found that in our system, if we consider a one-dimensional Moore lattice structure, meaning that the periodicity of different lattice structure in two rings are different, we found that the coupling between different layers is quite straightforward, meaning that the coupling between those two rings can be introduced quite easily. And we explored this feature and found that when we have a very small coupling between two layers, we can see dispersive band. However, if we increase the coupling strength at some threshold value, the system, the band structure become flat. And if we take one example here, we can see that all the modes are localized at a single frequency mode corresponding to different band. So one can selectively excite these flat band. One can selectively excite different frequencies corresponding to different bands. And this work shows that first of all, it provides a way to study Moore physics with few rings. And secondly, it can give us the idea that the flat band corresponding to the strong connectivity between different layers, and for different geometric ratios of the periodicity between different layers, the threshold can be different. And our work can show that in two large rings, it can have a small separated frequency mode due to the Moore physics, which can be used to excite frequency counts at smaller frequency spacings use large rings. So as a brief summary in this work, I show you our recent experiment result and theoretical works on the synthetic frequency dimensions. And at last, I want to acknowledge all my collaborators and all my group members and also the funding agency. And thank you very much for your attention. If you have any question, you can ask me through email. Thank you.
Okay, so we will skip the question part. Our next speaker is Professor Konstantin Dorfman from China Normal University, but now I think he's already transferred to Hainan University, right? And welcome.
Right, thank you. Thanks, Mr. Chairman, and thanks to Olga for the kind invitation. So actually, today I decided to speak on a different topic compared to the previous laser physics meetings, which basically where I talked about ultra-fast spectroscopy. So today the focus will be slightly different in the light of broad interest in the session in materials and topology. So I will talk a bit about metasurfaces. And basically, historically, metasurfaces are just a result of sub-wavelength ability to pattern materials. We basically started with a blazed grating, and after a certain refining, or I would say generation of technology, researchers were able to pattern things with a really sub-wavelength resolution. A lot of interesting physics and application came out of this ability to create various sub-wavelength antenna shapes on the surface. For instance, a celebrated paper on the Snell's law, where the phase gradient can be created on the surface, which can replace essentially propagating effects in the diffractive optics. And this phase gradient enters in the right side of the Snell's law. So interesting fact about these metasurfaces is that phenomena like a Berry phase in topology can be viewed here classically in the context of so-called Pancharatnam Berry phase. It's not really a topological phase per se, as is defined, strictly defined in condensed matter. It's rather a geometric phase, but for the consideration of Poincaré sphere and behavior of the as a topological phase, as off-diagonal element of some sort of matrix, it behaves pretty similar to how the topological phenomena behaves. In this case, the phase enters as the off-diagonal element in the classical transmission matrix of a classical field in a classical Maxwell equations. Nevertheless, this analogy is quite interesting and gives a lot of perspective of what can be done with the metasurfaces, and the spectrum of applications is large, from engineering applications and optimization of light transmission to quantum optics, spectroscopy, cold atoms, and so on. So in our group, the interest is to really apply metasurfaces to study something about complex systems. And for instance, what would be the benefit of using metasurfaces in spectroscopic studies? Can we use some of the parameters of the geometry or topology to study material systems? Are there control parameters which can be used? What does metasurface add to linear and nonlinear light matter interactions? Is there any connection between metasurface and the geometry and the temporal process in materials? Can we control not only the transmission but the photon statistics? Is there any relationship between this geometric phase or a proxy of the geometric phase, which is a macroscopic classical geometric phase, and the complex Berry phase of the material? So all these questions basically stimulated us to enter this field. And we started with bringing some basic perspective of Maxwell equation into the game. Using the Maxwell equations, try to analyze and expand polarization in the right-hand side, in the periodic structure with the fixed geometry and fixed rotation angle. And introduction of the propagation phase allows us to expand the field in this type of environment and calculate the transmission of the field by having this propagation factor. And the propagation matrix itself, as expected, contains a diagonal terms which conserve the spin, because only the sigma z enters in the unit matrix, as well as the off-diagonal elements which contains these phase factors due to the rotation of the antennas, which flip the spin, or because they involve sigma minus and sigma plus. So the interesting fact is that if we take the far field scattering and analyze its phase, we find a expansion over the periodic structure with a reciprocal lattice vector. And if we analyze the propagating wave conditions, and we use the fact that antennas are distributed uniformly such that the average of the simple phase factor vanishes, then we observed that only 0 and plus minus first diffraction order survives in the far field, which is confirmed experimentally. And moreover, the first and minus first diffraction term contains the phase gradient. In this case, it's a linear phase gradient, which enters the Snell's law, as has been demonstrated experimentally. So this is a quite simple analogy. Now, of course, if we want to extract the phase, we would like to do some kind of interferometric measurement, because generally diffraction orders of the higher order are weak, but we would like them to be on the same footing as the 0 order. So for that, a bit of optimization work needs to be done, and polarization conversion efficiency for cross and co-propagating polarizations should be equal. So some simulations in COMSOL allows us to find an optimum parameter regime, aspect ratio of the antennas, and distances to maximize the conversion and emulate a 50-50 beam splitter. So we asked our colleagues in Korea, in France, to take the metasurface and put it in the simple Mach-Zehnder interferometer and scan the metasurface across the beam to basically be able to capture various discrete phase gradient terms in the transmission beams. So after this 50-50 optimization, it's indeed a sophisticated beam splitter. And if we put the both beams after the Mach-Zehnder together and try to look at the transmission, we will observe a perfect linear gradient. And we did it for various metasurfaces, various sizes, and so on. It behaves perfectly linear as expected. So basically, this allowed us to connect some observable with the Pontcharrat-Berry phase in a very direct way. There has been a lot of discussion prior to 2020 about whether we actually observe the topological phase, or it's just a reflection on the propagation phase, which due to certain symmetry consideration shows up. So basically, this measurement was kind of a direct observation of this phenomena. So the next step, we took the nonlinear terms in the Maxwell equations to look at the something that we would like to apply for pump probe scheme. So it's a Chi3 processes, the third order nonlinear response. And again, using the same expansion over the unit cell and the same type of geometry, we have varied form factors representing the shape of the antennas, and the transmitted field as the result of the Chi3 process has the following transmission metrics. So as we see, the different polarization components accompanied by a different phase factors, and those phase factors essentially allows us to filter out the nonlinear response and use the polarization as a control tool to separate different components of the nonlinear response. As an illustration, we took a model system with polarization sensitive transmission. It's essentially a kind of a bi-exciton model with the X and Y dependent polarization transitions. And by looking at various diffraction orders, first and second, and so on, we looked at the specific components and combination of the susceptibilities which contribute to the transmitted field. And this T0, R, T1, and so on, these are the transmission amplitudes for the specific combination of polarizations. And A are the amplitudes, which are the combination of the third order susceptibility tensor components. So to look into the actually signal, we would like to take a specific combination of the three input fields. Let's say first one is linear X polarization, second one is right circular, and the third one is vertical linear polarization. We can then observe first and second order transmission amplitudes. And as we see, they all give a different combination of resonances corresponding to this bi-exciton model. Since the model is simple enough, we can really filter them out and compare with what we expect to observe specifically the all X chi3 and then pairwise X and Y susceptibility tensors, they're real and imaginary parts. And since the response is just a linear combination, we can do a data processing by combining these measurements to extract individual components to the susceptibility tensor and plot this real and imaginary part in this way. So, of course, the next step is to look at multiple dimensions, because if we really want to connect this with a real system, we would like to understand the role of localized and delocalized plasmonic charge densities. And if we look at the variation of the susceptibility tensor with respect to the pump and probe frequencies, or pump and the signal frequencies, then we see that these two dimensions give us diagonal and off-diagonal peaks, where diagonal peaks represent the localized plasmon resonance, and off-diagonal the oscillating delocalized or transient plasmon charge densities. So if we have a sophisticated model for the environment and maybe atomistic calculation for the energy structure of the material, we can really extract information about fluctuations in environment in this type of measurement, because each of these line shapes represent the environment for the specific plasmon polariton. So as a next topic where we try to look for quantum optical applications of metasurface, we look at a basic Bell state analyzer, where it's basically a combination of polarizing beam splitter and beam splitter, and it is well known as a no-go theorem that any combination of linear optical devices cannot distinguish a full basis set of Bell states. So we have 4 Bell states, symmetric and antisymmetric. And this Innsbruck scheme, this particular one is called Innsbruck scheme, is done by Zeilinger and so on. Basically, we can distinguish 2 out of 4 Bell states using this scheme, but not all 4. So in order to see if metasurface can help us with this type of distinction, we first try to derive an effective photon state, combining the linear and nonlinear propagation, which we discussed previously in the classical case. So now the fields are quantized, but the nonlinear interaction can be modeled through the effective Hamiltonian. We have k in and k prime out photons, which are incident and transmitted through the metasurface. And after a certain type of mathematical exercise, we get 2 terms in the effective photon state. One contains the G10 as a first diffraction order, another one is a -1 diffraction order. I will skip the argument why there are no other diffraction orders, but because the logic is quite similar to the one which we already discussed. Now, we can use now the so-called binary pixel metasurface, where the metasurface is composed of 2 types of pixels, and each of them contains essentially a dual layer phase gradient, such that any combination of EX and EY can be incident on this dual layer. And as the result of transmission, we can have EY EX or EX minus EY. If we take, let's say, the difference in the phase equal to pi between the susceptibility XX and YY. So this is illustrated in this phase distribution. And we can also take, odd number of pi over 2, let's say -3 pi over 2 or minus pi over 2, to create another type of phase gradient, so that we have EX plus minus I EY. So this I extra factor gives us distinction. So basically, if the metasurface is composed of these 2 types of metasurfaces, and we replace the beam splitter by this type of metasurface, we can observe some kind of variation and violation of the symmetry. Before that, we of course ran some microscopic simulations for specific materials, in this case gallium nitride on the sapphire substrate, and we made sure that it is possible to obtain certain type of phase gradient for the susceptibility components, and it's linear enough so we can really use it in a practical calculation. And this is indeed the simulations from the console, where we can see the various components of the phase gradient for this 2-pixel metasurface, and the far field transmission spectra, where we see this pi and pi over 2 phase terms. So yeah, basically as the result, if we put metasurface 1 and metasurface 2 in 2 arms of this interferometer, replacing the polarizing beam splitter, then we observe the interesting phenomena that depending on which ports we use for coincidence counting, we can either clearly separate the first first Bell state, or we have a combination of the other 3, versus the 2 and 2 in the case of the Innsbruck scheme. So since we have 2 measurements and 3 Bell states, it is possible for us to, with a single measurement, to get 75% efficiency versus 50 for the case of Innsbruck scheme. So we can distinguish 3 out of 4. And with one rotation of the polarizers, which are attached to the detection ports, we can do 100%. So, of course, this is just kind of a probe of the approach, and we are currently working on the more sophisticated schemes to maximize the input. And yeah, basically for the optimum parameters and rotation angles, we get this perfect anti-correlations of the all 4 Bell states. And yeah, this basically summarizes the work. So by measuring the, basically, of course, the question could be, what can we do to maximize the conversion efficiency to specific Bell state? How many different measurements we need to do to obtain the perfect statistics of perfect anti-correlation? What happens when the metasurface is not perfect? So currently we took pi over 2 rotation factors, these alphas. We have also calculation for which includes imperfection. Of course, the efficiency drops as expected. So in summary, we basically established a linear and nonlinear mesoscopic model to study the light interaction and scattering from the Pancharathna-Berry metasurface, established the role of the PB phase in the distribution of the transmitted light. We also proposed the spectroscopy for the pump probe to analyze specific transient and stationary charge distribution in multiple dimensions. And we looked at the Bell states as an application for the quantum state analyzer. And of course, as an outlook, some of the questions which were posted before, can we use metasurface to generate quantum light rather than use it for post-selection? Can we use the geometry instead of time to look at dynamics? That will be very interesting. Again, some of these things we have as an ongoing project, so hopefully next time I will report some of the progress. And finally, maybe the sacred question, I mean, is there really connection, and can we use the control of something like Pancharathna-Berry, the macroscopic phase, to control the microscopic Berry phase of material? So would like to thank the group. Most work is done by Zhang Jiegao here, sitting in front in the white sweater, and some of the work done by Jiang Sung, and our collaboration with Patrice Genevieve from CNRS. Currently, he started new position in Colorado. So on that, I would like to thank you and welcome all of you to visit Hainan. Most of the people don't need visas to visit, so if you enjoy the beach, please come and visit us. Thank you.
Thank you, Konstantin. Any questions? So, Konstantin, you use the, okay, Vitaly, please.
It's a very interesting talk. When you are doing this so-called phenological quantization of the field in the continuous medium, you also need to analyze the relaxation processes by including the reservoir of, say, environment oscillator. And in this case, you can describe the relaxation, depolarization, and other effects taken into account. Did you study or analyze these kind of effects and to see how your system, how clean or perfect your system?
Yes, thank you. It's a very nice question. So, as I said, we use the phenomenological losses to simulate imperfection in the transmission properties. This is just to demonstrate how efficiency of the Bell state analyzer drops when we include it phenomenologically. In the same time, we have another project which is ongoing right now, where we use so-called Davidov ansatz to emulate a strongly coupled material vibrations to electronic structure of the actual metasurface. So this is much deeper and much more microscopic analysis of the real material confined to a specific antenna cavity, which includes the losses, the spectral densities and phonons, and basically to properly take into account microscopic nature of environment. As of now, we have mostly phenomenological losses included in this particular work.
Okay, great. Thank you.
Thank you, Konstantin. Well, any other questions? If not, we have been 10 minutes after the schedule, so I would like to thank Konstantin and thank all the speakers. Thank you.
Thank you, Davey. And let me remind you that in 10 minutes we have our plenary session. Please welcome. Thank you. Good morning, Shaw.
Yes, good morning. How are you?
I'm fine. How about you?
Yeah, good, good.
All right.
Yeah. So, yeah, so the meeting is really interesting and going well. Yes, yes.
Thank you.
Yes. It's a lot of material and it's really interesting. Yeah. I will do the letter today. Yeah, there was a confusion about so.
Yes, 2 places where to put, but the same letter, just in 2 places. Yes.
Right. That's what I will do. Yes. Yes.
Great. Thank you.
Yeah. Sure. So, how many people are typically attending? Yeah.
Well, our seminar is quite active. Typically, we have in our seminar about 30 people.
Oh,
sometimes. Yes, yes.
That's nice. Yes. Yeah. Good. Yeah. And you know, I was intrigued in our last discussion about, you pointed out to me that really they did not observe the Rabi splitting in the X-ray. And so hopefully somebody will be able to do it. Yeah, yeah.
Not very soon, I'm afraid, but sometime, yes, yes.
Right, right. Yeah. And your X-ray work, you know, you have been working on the high resolution measurements for the X-ray.
Well, the most recent is what we did is exciting of very narrow nuclear resonance. Yes.
Yes. Yes. Yeah. Right. Right. Which is
should be published soon in Nature.
Yeah. In Nature?
Yes. Yes.
Oh. So this is together with experiments?
Yes, that's right. Yes.
In Germany, the German group?
Yes, yes, correct.
I cannot pronounce his name. Yeah.
Ralph Rasberger and Yuri Shvitsko from the Aragon National Laboratory, who was leading the project. Yes.
Okay.
Remember. Hello, Rainy. How are you?
Nice to see you, Olga.
Nice to see you.
Hi.
Are you still in Snowbird, or is this just the background?
Well, I would like always to be there. Better than in hot Texas.
All right. Hello, Carlos.
Hi.
Hello.
Hi, Olga.
You can already share your screen.
Okay.
So that we see if it works.
Yeah. Should work, yeah?
Perfect.
Yes,
great.
Perfect. Yeah.
Great.
All right. I think we still wait until the full time so that people can join.